Very warm welcome to everyone and good evening. It's my great pleasure to host. Thank you, Professor Prem Kumar, for making your way to IIT Bombay. We are very fortunate that he's going to speak to us about engineering challenges for emerging quantum networks today. So I'm going to be very brief in introduction because it's a very long history of things that he has done. Just to begin with, he's a professor of information technology in McCormick School of Engineering in Northwestern University. And his career has spanned from various activities, including academic and academic related, but on the other side of the bench, in the funding side, working in DARPA. He's also a fellow of various different societies, including Optica and IEEE, APS, AS, SPIE, all of it. And anything that you wish for, he is a fellow of that. And I think there are several awards that he has won, so I am really not going to bother too much in giving you details of all the awards that he has won. And what I would like to say is definitely one of the most inspiring scientists that I have interacted with in the, through my PhD a little bit and then over now much more. Definitely it's a lot of learning, seeing how his career has evolved over time and how we can evolve, in similar fashion. Now, one thing I would like to also mention is that he is also serving as the editor for Optica Publishing Group currently, and it's also another different aspect that one can contribute in your scientific career. So it's a diverse range of things that he's been associated with, and I'm very happy and very fortunate to invite you to give your talk today. So please, thank you.
Thank you, Kasturi. Thank you for the warm welcome. And I have to say that this is my first visit to IIT Bombay, and it's so far been a pleasant one. And I'm humbled in some ways. So to be here and talk about some of the things that have been quite exciting for me, and I think things that have a very bright future. So I want to present to the students here, because I think even though we talk about quantum networks and quantum computing and quantum XYZ is very popular these days, I'm sure everybody heard about the National Quantum Mission, and we have National Quantum Initiative in the US, and every country you can think of has a quantum mission. And many of these technologies have a very long horizon. So this is really for the students, because chances are breakthroughs will occur during your lifetimes and possibly not mine. So with that, let me begin by giving you a flavor of first, what are emerging networks, quantum networks? And before that, what is a quantum network? And before that, what is quantum communication that connects quantum devices together? And why do we want to do that? Okay, so that's kind of where my introduction would be. And I want to paint a very big picture, and then hopefully then towards the end, talk about some of the contributions that we're making. It's a long road. Okay, so with that, let's move ahead. This first slide sort of paints a very high-level picture of what we enjoy today, what's been called the bit revolution. Right now, we're presenting in an electronic form. It's been streamed on YouTube, probably seen worldwide, everywhere. We're in a stage where we take communication and computing, ubiquitous availability of communication and computing for granted. And we didn't get there overnight. It took 50, 60 years to get there. So this slide, in a way, captures, early on in the 1940s through 50s, people started to build computers. Actually, that's not the beginning of computing, right? Because people had mechanical computers before that. A lot of things about computing per se, the theoretical foundations of computing were done in the 1940s and even before that. However, technologically, things started to take off when the transistor came on the scene, integrated circuit was formed, and people started to make small-scale computers. And there were visionaries at the time who started to ask the question, what would happen if we could interconnect these small-scale computing devices together? And there was this ARPANET that you may have heard. There were visionaries like Vint Cerf, Bob Kahn. These are the people who are called the internet evangelists today. They wanted to see what would happen if you could interconnect small-scale computing devices. The goal at the time was file transfer, email, message communication. But 50 years later today, everyone, every child, even a 2-year-old takes email for granted, right? So it's in everybody's hand. Those kind of early demonstrations of networking turned out to be very important, not because there were devices at the time that would lead to ubiquitous connectivity, but it allowed people to think about a network as an abstract entity. How should we architect it? What protocol should be executed? How should we manage it? So that led to, for example, this TCP/IP protocol, this transmission control protocol, internet protocol. Those who are in the computer engineering probably know this very well. And people started to build models of networks that today it's more like this kind of a model. This 7-layer model that you learn in your textbooks is very different. It's than what we practice today. Even the nature of communication today is much more modern. Optical communication is very, very similar to wireless communications, but that was not the case, let's say, at the turn of this century. So the point here simply is that people started to build network, ask the question what the abstractions for devices should be so that we can engineer devices accordingly. What devices is needed in the near term, what devices are needed in the long term, so we can prioritize research and then make progress. And then in the 70s, a lot of prototype networks were built. And today we live in this age of cloud computing, big data, AI, and that's what makes connectivity computing ubiquitous. And today it's artificial intelligence, it is large language models, and what computing will give us for tomorrow. So that's sort of the history of classical bits. I label this as bit revolution, but there's something else happening these days, which is what I would like to label it as qubit revolution. We are in those early days of quantum information processing. So from a networking perspective, again, the story of it goes back to early this century when people had been thinking about quantum computers. In the early days, quantum computing research was kind of hijacked by this Shor factoring algorithm. It has a historical context I don't want to get into here, but nevertheless, there was emphasis on quantum key distribution, and people started to build networks of, can we do in a network setting distribute quantum keys and things like that. But then along the way, the size of quantum computers was scaling as well. They were getting bigger and bigger. And then, you heard about this quantum supremacy experiments where quantum computers are getting large enough that it's very hard to simulate the behavior of a quantum computer on classical computing devices. So, but one is finding that scaling quantum computers to do useful things is hard. That is, every quantum company, and this slide is a little bit old, so I have not captured here all the quantum advances that have occurred, but everyone thinks that the progress to scalability is through modular systems. That is, systems that interconnect to make a larger computing substrate. So that means that we need to figure out how to communicate between different computing nodes. So we are in that early stage, like in the classical networking, in the quantum networking, or in the quantum communication / networking. How should we architect a quantum network? What it should be? How should we operate it, manage it, and so forth? And more importantly, what should the device abstractions be? Because the technology is not here. Can we learn? Can we create that churn of protocol architecture devices so that we can make progress? And so that's the motivation for working in these emerging quantum networks, because we realize that computing will be hard to scale. Quantum computing would be hard to scale without bringing in the network elements in it. Okay? So that's the very overall high-level picture. And what then for the students, I want to go back to the drawing board and start from the beginning. First of all, what do we mean by communication? What do we mean by quantum communication? And what is a network, and so forth? So let's step back and ask the question, what is classical communications and networking? And at a very high level, two parties want to communicate. I'm talking classical communication now. And this could be your handheld device. This could be your Morse code, on off dot dash, or it could be your modern iPhone. In the end, there is a communications register, and these dots are meant to represent bits, but these are classical bits. They can be in state 0 or 1. Bob, on the other hand, has a similar device, a handheld or whatever. And Claude Shannon taught us almost 60, 70 years ago, in the late 1940s, that irrespective of this channel that connects the two parties, it is always possible to do error-free communication below a certain channel capacity. It took a very long time, almost 40, 50 years, to invent the codes that are needed for this efficient communication. And today, error-free communication is ubiquitous, right? And of course, Shannon played a big role in secrecy systems also. So communication and cryptography in some ways goes hand in hand. So with that, we asked the question very naively, can we extend that? Actually, before that, it is ubiquitous in the sense that a supercomputer of today or a data center is essentially a very large network of classical computers. Communicating with each other, algorithms are parsed in such a way that parallel computing is very, very efficient. The whole world, first it was just electrical communication, then optical communication. Today, the whole world is wired with fibers. And last mile connectivity is usually wireless, and you see these sort of, I call them metallic trees that you see everywhere. Those are your wireless towers. And pictorially, the world is engulfed in fibers. Okay, so then we ask the question, what is quantum communications and networking? Now, instead of two parties, Alice and Bob, having a classical register here, imagine now they have a string of qubits. A qubit is not just simply two states, voltage high, voltage low, or a photon polarization, horizontal or vertical, but in addition, a qubit can have a quantum state that's a superposition of that. So pictorially, we represent this with a Schrödinger's cat, something that's in a superposition state, simultaneously alive and dead. That's just a pictorial representation. And we ask the question, if the two parties are connected through some quantum channel, under what conditions can Bob have that quantum state that was in Alice's possession? Of course, you can transmit that physical entity, let's say a photon or a particle or whatever it is, directly take from Alice to Bob, but that's not very satisfactory. Alice and Bob have to be very close. But if we naively say that we can communicate that, the same state on Bob's side, then we find that we're already in conflict with the fundamental notions of quantum mechanics. Because if Alice had this state and Bob also had that state, now you have two copies of the state. And that clearly violates the no cloning theorem. We can also say, okay, what if Alice measured her state and transmitted the information and Bob could recreate that state? That is also not possible because we have Heisenberg uncertainty principle that you cannot measure a quantum state precisely. So anything that we can think of normally in communicating a quantum bit from Alice to Bob runs into conflict with quantum mechanics, and if we can transmit it, but it normally is restricted to short distances. However, things changed quite a bit actually in circa 1993 when this teleportation protocol was invented. So Charles Bennett, then at IBM, and still IBM, I think, and a whole bunch of co-workers came up with the idea that if Alice and Bob can pre-share a new resource, a new resource of entanglement, it's simply like, two parties want to have a shared secret in some ways, right? Classically speaking, if you have shared set of random bits, you can securely communicate. So it's that kind of a notion. If there is a new resource of entanglement, let's say an entangled pair of photons, one photon in possession of Alice, another photon in the possession of Bob. And if Alice wants to communicate a bit, like I showed in the previous slide, she makes a special type of a measurement. We call that a Bell state measurement. It's a joint two-state measurement, which has four possibilities. Either qubit is high or low. And that's represented by 2 bits of classical information post-measurement. And if she can simply classically communicate that to Bob, turns out that using that information, Bob can convert his part of the entangled pair of bit into a state that post receiving that message is exactly the state that Alice wanted to communicate. In the process of making that two-state measurement or joint measurement on those 2 qubits, Alice's state is completely destroyed. So it's like the state appears in the possession of Bob's particle, previously which was in Alice's possession. So this kind of obviates those difficulties with quantum mechanics that I showed in the previous slide. And this kind of a new resource, if this can be pre-shared between users, of course that also means that they have to have those entangled shared states, they need to store them. But if you can do that, then at the time of communication, Alice, all she needs to do is to do a Bell state measurement classical communication. There is no need for a contemporaneous quantum channel. So sometimes people call this kind of communication a connectionless communication. You drop on your resource and you communicate quantum states. It turns out it is quite challenging, as I mentioned already. You need this ubiquitous availability of entangled photon pairs. That means efficient sources of photon pairs, also distributing them in such a way that the entanglement is preserved. You need to have these technologies for storing that entangled photon pairs. That quantum state of the photon is stored at Alice's side, the other pair on Bob's side, and they can not only store but recall whenever they need it. So it's a very, very tall order from a technological perspective. And then, Bell state measurement, it turns out that optically it's very hard to do. You can only still do partial Bell state measurements. You can't really unconditionally measure Bell states. And of course, in the process of distributing entangled photons, there are losses in the fibers. Even though fibers are very low loss, but they restrict ourselves to metropolitan scales. So, in classical communications, with the advent of the optical amplifiers, it's global communication we have. And the question is, how do we get there? And people talk about the concept of quantum repeaters. Those are the kind of things that we still don't know how to build. We have notions, theoretical notions of how to build, but we don't have an example of a quantum repeater that even works in the lab yet. So with that high-level introduction, we talk about networking. So as I mentioned before, there is a case for networking because every computer company these days, if you talk to, in their scalability, the argument is that the quantum computers need to be modular. You just cannot scale them right now to the level of the number of qubits and the so-called quantum volume, or whichever way you quantify the progress in quantum computing. The notion is that they need to be, one need to be able to interconnect them. And this is an old slide. It makes a case that yes, as you scale quantum computing, how do you verify? But that's how the situation has been for hundreds of years. You verify things by experimentation, and perhaps something like that would need to be done in the quantum domain also. But nevertheless, the case is in this last point here that if I can make in a cost-efficient way n-qubit machines, but m of them, then interconnecting them with just classical communication will only give you access to a Hilbert space, whether your algorithms can access in a practical device or not, but there's an upper limit of m times 2 to the n. On the other hand, if you can interconnect them with full connectivity quantum mechanically, you can access the full Hilbert space of 2 to the n m. And there's a huge gap between the two. And so taking quantum machines and learning to interconnect them quantum mechanically, that's what we've been calling quantum networking. Okay? And rudimentary pieces of it, technologies are developing. And here's an example of distributing entanglement that the Chinese have implemented in this Messier satellite. In their satellite is an entangled photon pair source, which is based on a periodically poled KTP crystal. This is, some of you may not know what that means, but nevertheless, take a course in Professor Saha's class and you will learn all about it. But my point is that this source was actually invented by Franco Wang, a colleague of mine, in a project that we were working on together. So this is a technology that was invented long ago. The Chinese engineered it and put it on the satellite, and all of a sudden entanglement distribution became very fashionable. Not only that, and by doing this satellite-based distribution, they could show that they can do entanglement distribution over distances that with fibers are not accessible at all. Moreover, other countries figured out how to engineer quantum systems. So here's an example. I thought this was very striking. This is quite old now, actually, from a decade ago at least. So this thesis is 2018, 6 years ago. In Singapore, there's a company that used these CubeSats to build a QKD device they wanted to fly and put it into orbit. And what happened is that they chartered a private space company, put it on the rocket, and upon launch, the rocket exploded. And but they were able to, from the wreckage of the rocket, they were able to extract their system. And what they showed is that this system was so well engineered that it could survive a rocket crash. And so there's red and blue are the performance of this correlated photon source that's in this box that was in that CubeSat, and it survived an explosion of the exploding rocket. So the point here being that the technology has gotten to a stage where we can think about engineering entanglement sources and putting them on satellites, taking them out of the field and building real systems out of it. And then having such kind of technologies, one wonders then, from the perspective of quantum communications and networking, what would a network of the future look like? We can ask the question, how would we internet a quantum internet. I write internet with a small I. The big I is a long ways off. But nevertheless, what kind of a network structure would it have? How would we determine those layered structure? Would entanglement distribution be one of those? And how would classical and quantum channels coexist? And in the context of entanglement distribution and teleportation, those 2 bits of measurement you need to communicate classically. So somehow classical and quantum has to coexist. And then, turning that into a business model, operationalizing quantum networks. So there's lots of questions, and there was a workshop held at NIST in 2017, right after I left DARPA, and I presented this slide kind of in a vision into the future, what might we want to do, and of course these are very speculative. How technologies will emerge and evolve remains to be seen. Okay, so while this was happening, the Chinese satellite experiment, ruffled a lot of feathers, not just in the US, everywhere. And, the end result of that was in the US, there was this National Quantum Initiative Act. This was during the first Trump administration. This is Michael Kratsios, I guess. He is now the science advisor to the president, so incoming science advisor, taking the place of what R.P. Prabhakar was. And clearly you will see that since it was something that originated in the previous administration, chances are very high that this kind of emphasis on quantum technologies in the US will continue. And you all know here of the National Quantum Mission, and this is a hub for quantum sensing. So there's a lot of things happening in this area. And so at the time, when things will be talked about quantum communications and computing, and the National Quantum Initiative in general, which has focus on computing, sensing, and all those things, just like in the quantum mission here, my lab, I was in the process of rebuilding, and we started to focus on quantum communications and networking as our chief goal. At the time, we partnered with 2 national labs in the Chicago area. One is, the picture here is the Fermi Lab. If you are in the particle physics area or high energy area, you probably are very familiar with it. We also have an Argonne National Laboratory. In this case, the project was led by Fermi Lab, but it's a partnership with Argonne and Caltech and a few other universities along with Northwestern. Our goal at the time was to go beyond what point-to-point links. So, what the MISIUS and the Chinese experiment was in the context of quantum key distribution, and we wanted to go, as I've said before, beyond just communicating cryptographic primitives, but also to be able to, on a path to connecting quantum computing, sensing, or other devices in a network setting. So instead of point-to-point links, we wanted to go to a repeaterless, because we don't know how to build repeaters, so everything is restricted to the metropolitan scale. But learning how can we create a network, an architecture that can drive device development, that can drive this churn between abstraction and physical devices. So that was the focus for us. And here's a network that you may have seen in China. Is probably the biggest quantum network. But this is again based on QKD with trusted nodes as the baseline. We don't want to repeat that. That's actually in our project. So here's the topology that we put together. Again, this is at a very high level. Some of this stuff is already in print and published. And if you're recording it, you will see what the references are in here. So basically, this what we call Illinois Express Quantum Network. It is a metropolitan scale network. It has 3 local area networks that interconnect. And each local area network, one at Fermilab, one at Argonne, and one at Northwestern, they have multiple nodes. That doesn't mean that all these nodes are populated. we are constrained in how much money we have to buy devices and stuff. So not everything that I've displayed here is actually populated. But nevertheless, bits and pieces are here, and we're growing this network to learn about the architecture, how to actually manage and control this network. Physically, it looks something like this. So it has small scale connections in the downtown Chicago area, long scale connections. The long here is probably 50 kilometers. So this is not very long in the sense of classical long haul networks, but it is still long enough that from a quantum perspective, it is quite far. So for example, I can bring light from Argonne to downtown Chicago to the Starlight facility to my lab, and this leg here already has 30 dB loss. So there's absolutely no way that I can implement anything quantum related here because there's too much loss. But nevertheless, I'll show you results on this leg here. We've been doing entanglement distribution, teleportation, and some of the things that you may have heard recently in our work. So from here on, it's just snippets of the current work. So I want to pause here, and if there are any questions in terms of big picture overall things, and if there are any burning questions, I'm happy to answer now. Otherwise, I'll continue. Go. So the use case, the biggest use case is to interconnect quantum resources. So whether it's distributed computing in the quantum sense, or it could be a quantum sensing network, a sensor network, for example, where you have sensing elements whose outputs are quantum states that you need to communicate to a joint for making some joint measurement. So that is the big picture. Along the way, our focus is not really on quantum cryptography because at least I feel that quantum key distribution is an example. Yes, it's an interesting thing to learn, but it's not quite clear how useful it is in a real network setting. So our focus is more on interconnecting quantum devices of one sort or another. Yes.
Sir, if creating a quantum repeater, would one potential design be like having the transfer protocol using entanglement within the same device, where the transmitter and receiver are both the same device? What are the problems that might be?
Yeah, I think the issue with quantum repeaters is that you need. Well, it depends on which generation of quantum repeater. People talk about generations because their architectures are slightly different. In the first generation, it's basically entanglement swapping that requires quantum memories, and the quantum memories are not very good right now. Yes, you can have quantum memories. You can take a quantum state, store it. The best quantum memory is actually quantum computed, the bits that are in a quantum computer. But from the perspective of photonic storage and recall, the quantum memories are quite limiting at this point. So unless and until the quantum memories get better, entanglement swapping to create a long haul link is quite challenging. I think we're not at a stage where we can say that, okay, here's a metric that we should compare the performance of a classical versus a quantum network. Right now, most of the things are in that initial demonstration phases. So the biggest thing that we've done in my lab recently is, can we do quantum communication, like for example, teleportation, in a fiber that already carries classical communication signals. And I have a slide on that. The reason being that, if we want to build quantum networks based on fresh new fibers that don't have any other signals, that's going to be very expensive, right? Because fibers are fibers. Usually, the cost of installing fibers is laying them in the ground. And if I've invested in, making fiber links, I want to make money on that, right? So it's the cost of leasing that fiber to run a single photon through it or a few bundles of photon is the same as sending trillions of photons through it. So this issue of networks that are solely built for a few photons is probably just a intellectual curiosity. It will never be in a field environment. So I think for me, it's important to learn how do you actually build networks that quantum and classical coexist. So those are, I'll talk a little bit about that. So we've been focusing on that. Any other questions? Yes. I'm sorry? Say that again? Yeah, those are just transparent optical switches, basically MEMS. So they're not repeaters. So it's like a array of mirrors. You can switch it to route photons from one to the other. So they have small amount of losses, but they're just simply mirrors that direct light beams. Okay, so again, we've a little bit about the architecture in terms of how our network structure is. It's more or less a 3-layer model, very similar to the networking, the software-defined networks that people talk about in conventional networking. So there's a physical layer, and then there's a link layer, and then some kind of a application layer. The applications so far are just simply entanglement distribution, teleportation, and things of that kind. Okay, so now I want to go into some examples of the work that we've done in recent years. So this is the case I already made verbally. Basically, if you want to do simply quantum communications using dark fibers meaning only quantum signals are on it and nothing else, that proposition is quite expensive. If we can figure out how classical and quantum can coexist, then there is chance for bringing quantum networking from the lab to the field. And this actually was clear to me long ago. In fact, this is an experiment we did in 2006, where back then we had generated this fiber-based photon pair source based on the spontaneous four-way mixing nonlinearity in the fiber. And we showed that you can send one photon of the signal idler pair. You can multiplex it into a 50 kilometers of fiber with classical signal. Classical 10 gigabit per second data carrying signals. And the other one having another channel co-propagating on the other side, with channel plan being here. So this is our entangled photon pairs on specific ITU channels. And these were depending on the lasers we had at the time, one actually propagating very close. Sorry, this is my alarm here. So the other one, propagating right next to one of the lasers, and the other one the same fiber but not too far away. Everything in the C-band here. And we showed that even after 100 kilometers away, classical and quantum can coexist, so that your two-photon interference visibility is still very, very good. And the reason was that we were able to maintain very high quality data rate at 10 gigabit per second, but we had to turn the power down a little bit to avoid Raman scattering. And so that I knew that coexistence is possible, but it wasn't quite clear at the time that what would it take to actually go beyond simply correlation measurement to entanglement distribution to actually teleportation and so forth. So it turns out that the Raman scattering in the fiber is the biggest limitation. And shown here is in two types of fibers, dispersion shifted fiber and standard single mode fiber, the effect of Raman scattering. So this is in terahertz. So this is 10 to 2 times 20 terahertz here and away from the central pump. So if 1550 is here, then the O band for the fiber, if you go that far away, it turns out that there is very, very little Raman scattering there. So that became our architecture choice or design of coexistence of quantum and classical. And this has been known actually in the classical QKD. In 97, there was an experiment done by Townsend. And then later on in the QKD networking context, that to do quantum key distribution in conventional optical networks. So it's not a new idea, it's been around, but we want to go beyond just simply weak coherent states protocols for quantum key distribution, but to protocols that can interconnect quantum computing node or sensing nodes. So we did quite a bit of work as part of this ICNet project. Now, the other new thing that one has to worry about in quantum networks is synchronization. Anyone who has done any work with classical communications knows that when you're sending a high stream data through a channel, the first thing you do at the receiver is clock and data recovery. Basically, you can recover the clock, and once you have a good local clock, you can parse your data no matter what kind of a modulation format one has to choose. So, but in quantum cases, to do the same thing requires much more because you have photon pairs. Your one data packet may be going to one direction in a network to Alice, located whichever node she's at, and the other one going the other way. And if you do local clock recovery, but you still have to synchronize those two recovered clocks. Okay, so you need to do more than simply clock and data recovery. You need to have some kind of a global synchronization also. That is, you need to communicate classically. You have to discipline your clocks at wherever locations the data need has to be. So we did some work to show that yes, by combining classical optical signals with your quantum signals, you can recover a clock from based on that classical data such that you can synchronize signal idler photon pair detection to a few picoseconds. Also, then some work in the context of entanglement distribution. This is now following a quantum channel in the O band around 10 nanometers and multiplexing C-band classical traffic. In this case, for this work here, it was published in Optics Express last year, late 2023, where we multiplexed all different kinds of C-band, L-band channels, but classically modulated just to send raw power through it to make sure that how tolerant these quantum signals are to spontaneous Raman scattering in the fiber. And we showed that actually you can design networks very robustly that can send entanglement over a fiber that's goes to from Evanston to Chicago and back almost about 50 kilometers. And you can maintain entanglement distribution with high visibility polarization qubit being measured. So this is a 2-qubit tomography on a polarization state that is multiplexed with these C-band signals and after 50 kilometers. And what we learned is that there are actual wavelengths that are preferable over even in the O band. And that is because, one would imagine that by now Raman scattering in fibers had been well understood, and that is indeed the case. Because, Raman amplifiers are used ubiquitously in long haul, communication networks that are undersea. Raman amplification is common. But those things have been engineered in the gain band, where the gain occurs. People haven't studied really far away from that gain band what is the characteristic of light scattering. And it turns out that there were the models that exist do not really predict actually what the Raman scattering is that far away in detuning. So in that paper that I showed you here, again listed here, the archive version of it, we very carefully studied how much Raman scattering is present far away from the C-band, if the C-band is populated with different wavelengths of light. And we discovered that there are quiet zones. Just like, in atmospheric communication, you find there are wavelengths that are much more transparent because of the nature of pollutants in the air. The same way we found that there are particular wavelengths that are actually much more scattering free from classical signals that may be present in the C-band. So with that, that led to this teleportation experiment that somehow has caught the attention of people. I don't know why, but nevertheless, it's an experiment which we create a correlated photon source that heralds a qubit. This is a polarization qubit. Upon the detection of a single photon from a pair source, Alice prepares a polarization state. And Bob has an entangled pair source, and that one of the photons comes to this mid station, which is the where Bell state measurement occurs. So Alice's qubit goes through L1, kilometers in this early experiment, 5 kilometers of fiber here, 5 kilometers of fiber here, and all the way through, classical light carrying the actual internet traffic is flowing through. So in the final version that we published in December, this was 15 kilometers of fiber here, another 15 kilometers of fiber here. So Bob's entangled photon, one pair of the entangled photon, counterpropagated with this 18 dBm of C-band data carrying signal over 15 kilometers, and Alice's qubit traveled co-propagated over that same amount of power to this middle station where Bell state measurement was made. And in these, so you have to make this Bell state measurement, that's a 2-detector measurement. Alice has to herald her polarization photon, so that's another measurement, and then Bob has to verify that the polarization fidelity is the same as Alice teleported. So this under 4-fold coincidences, you show that the state actually appears at Bob is the same state that Alice prepared. So you verify that through various measurements. So here is the 4-fold coincidence rate. As Bob's photon in Bob's possession's polarization state is varied, and so one is for the diagonal state being prepared by Alice, the other one is the anti-diagonal state, and they are 180 degrees apart. And it takes a long time actually to do these measurements. So these are, each point here is 300 seconds of data runs because the entangled photon rate is very slow, and this is 4-fold coincidences. So it takes a while. And then the average fidelity, irrespective of what state is chosen by Alice, exceeds this classical threshold. So this paper done in collaboration with Siena, who actually gave us that 400 gigabit per second, this very modern transmitter-receiver pair that we use for actual data traffic that goes along with the fibers. Along with these qubits. Again, this kind of technology is quite robust because this is some show floor demos we did very similar to those. You can launch these in satellites. They're very robust. You can package this up and go to a conference and make demonstrations of entanglement distribution and coexistence. So this is something that we partnered with Quantum Opus and the switching company that somebody asked me a question on, and we demonstrated in the presence of classical channels in a show floor environment at OFC that yes, you can, this is not now a lab thing, you can take it out and actually do something in real world. As part of this work, we've built a network at Argonne Labs. So as I said, there was those local area networks. So far I showed you the work on the northwestern end of things. There's a network that is being put together at Argonne. It's called Argonne Quantum Network. And we've done entanglement distribution there. The distances are, in this local area network, the distances are smaller. But nevertheless, it's very easy to distribute entanglement over various different locations. The next step in these is we have a new project where you want to distribute entanglement between various different qubit modalities. So the goal here is to build first version of a repeater entanglement swapping kind of an experiment, which also involves quantum frequency conversion and other things that I have not included here. but this is a project we call InterQNet. That's a project that we're currently working on at Argonne. I want to take the last few minutes to talk about control and the question of how do we actually manage a network, how do we control a network. And that's going to be important if future networks are going to be ubiquitous like the classical networks today. And we envision what we call quantum wrapper as an idea for controlling networks of having users share the same quantum infrastructure, but in a manageable way, in a shareable way, by enclosing a quantum payload. And again, I'm imagining fibers here connecting various users in some kind of a setting, and there is a software-defined management and control system that can control these various switches that I was mentioning before. But they are done upon measuring what we call quantum wrappers. These are classical bits that are ahead of a time slot that has a quantum payload. By measuring those quantum bits, one can have embedded in them a whole lot of information. That could be routing information, that could be destination information, quality of service information, that could be this quantum payload has bits, what type of entanglement are they carrying, or what are their entangled partners, at which nodes they are, and things like that. So by wrapping a quantum payload with classical information, we can make not only you can write in a packet switch network, for example, where the packets need to go, but also infer based on the health of those classical bits what might be happening to the quantum payload. Because as you know, in quantum networks, as I mentioned before, you can't really measure the payload, right? So, but we want to infer what the health of that payload might be. And if, for example, on one path, in one path, if it so happens that somehow the noise is more, or maybe there's another classical signal flowing through that's contaminating that path, then by looking at the nature of that classical payload, you may want to switch and route to a different path. So these kind of things are possible in this quantum wrapper networking protocol structure for management and control. So we think of this as kind of the TCP/IP equivalent of what a classical network is. And we're experimenting with that. So here's an example of an experiment that we did in collaboration with Ben Yu's group at UC Davis, his student and my student. We had limited resources in terms of we only had one entanglement source and one pair of detectors. So we kind of time division multiplexed two payloads with two headers. And then depending on we had a 1x2 optical switch here, and based on that, but using this multiplexing scenario, we showed that indeed you can read a header off and direct your quantum payload from one destination to the other. And later on, we've recently done an experiment where you're monitoring the header continuously, and if somehow its signal to noise gets worse, you know that something is happening in that path, and you can switch and route to a different path. So here is an example of the time division multiplexing. So there is an HV state on this times in this time window here, and there's an HH state in this time window here. It's blown up, and you can see that we can switch and route with high fidelity upon measuring the classical headers. In this experiment, you can also basically use, in this case, wavelength division multiplexing to extract the header out, make a measurement on it, and then have a switch for the quantum payload. While the measurement is occurring, you place the quantum payload in a delay line so that when you've deciphered the switch, put a new header on and remultiplex it again. So these kind of ideas, again, this is classic basic engineering of quantum classical coexistence. And so that's the work that, that we are currently pursuing from a practical point of view. There's some other work in my lab which has to do with electronic photonic quantum integration. This is some joint work with people at Boston University and UC Berkeley. The idea here is to, can we control quantum devices which are integrated? So basically this is silicon photonics, very much similar to what you might have worked on. But here, this CMOS is actually true zero change foundry level CMOS. The transistors are actually right on the chips. Okay, so in fact, it is the rings are on the same die as the transistor circuits are. So the heaters that control the flow of these photonics systems are controlled by transistors that are right on the chip. And this is some work that is currently under review at Nature Electronics. So hopefully this will come out. So I have some old video here, which shows that as we ramp through this ring, you find a lock point, and in the next iteration you lock it, and you can see that the rate of the correlated pairs stabilizes, the signal to noise, that is the coincidence to accidental ratio, stabilizes, and it's done online. And if you send in another signal to another part of the circuit to perturb that, it captures it back. So there's onboard control that's in this system. And there's a lot more to be done in this. The idea here was, we need to be able to integrate classical control into devices that can be put together into small form packages and develop technologies for quantum networks. So I think with that, so just again, I give you a flavor of what my lab is doing. Towards the end, I know I've rushed through, but if you have any questions, I'd be happy to give more details on that. With that, I want to summarize. I think the outlook for quantum networks is pretty bright. I think quantum computing is going to be a leader. And as quantum computing, irrespective of what platform it is, as progress occurs, every quantum computing modality asks for modularity. And in order to serve that modularity, I think we need to learn to do quantum networking. Whether that's chip to chip, board to board, chassis to chassis, or room to room. I think these kind of things we have to learn and implement and make test cases now than to wait until quantum computing stalls. With that, I'll stop here. Right. So I think there are many examples in which if you simply, let's say sensors are some kind of transducers, right? So I imagine that that whatever is being sensed, whether it's electric fields, magnetic fields, pressure, temperature, whatever have you, and those light pulses, beams, whatever, if you just classically transport them and make measurements, you find that you can do much better if those quantum states are brought together and a joint, more exhaustive measurement, quantum mechanical measurement is made. So by doing that, you can do much better. So meaning that you can sense things that classically otherwise are not possible. So one example, an ordinary example is LIGO, gravitational wave observatory, in which by injecting squeezing into an interferometer, actually you can increase your sensitivity by a lot, depends on how much squeezing is installed in. Same way, if you have sensors that are trying to sense a common signal. So one example could be, I mean, gravitational wave detection is one example, but similarly, let's imagine you have microwaves coming, and I have optical sensors, little chips with electro-optic things in it, and if I can take those modulations of electric fields and I can jointly process them in a quantum mechanical measurement, I can do much better in sensing that common mode signal. So that's an example of what we would call quantum sensing that goes beyond classical. So the networking part there is basically, in that sense, I would say it's a passive network in the sense you're just transporting quantum signals, bring them to a local station where you can do joint processing. But the measurement you want to make is that, so the fidelity of the quantum states as they come over that network is important. Because if that fidelity of the states is not maintained, your joint measurement is not going to be reflective. It may not have that quantum advantage. I hope that answers that. I mean, I'm still not quite sure. If you have, we can discuss more. So that was just a drawing. I mean, it's, yeah, in principle, you can get away with it. The point is that there is still a little bit of Raman scattering. Maybe there's some customer may want really a dark fiber, right? But yeah, it's just notional. No fundamental reason, yeah. Yes.
One of the slides you had a qubit transmitter and qubit receiver. Is that something you buy off the shelf or you made something? Understand how it looks like.
So a qubit, I think, so there are many people selling, many companies selling these things, and so here's an example of a box. So at least, so this is the entangled photon pair source. These are some devices that do polarization control. So it's something that you can engineer into a box.
You can buy it off the shelf.
You can buy it off the shelf. I mean, it's limiting, but there are. I'm sure technology will proliferate and.
But that's what you're using to demonstrate.
Yes.
Quantum entanglement.
Yes. Yeah. No, that's the point, that you don't. Right. So right. So the point would be that if users are going to share the quantum channels, then they have to share in some way, whether in traditional sense, that they have to time share or they have to wavelength share and so forth. Yes. Yes. Right. So dark fiber traditionally means is that the only thing on that fiber is your quantum channel, nothing else. Yes.
You just mentioned about wavelength sharing for multiple quantum systems. How would demultiplexing take place in the institute? Because if I'm not wrong, the example you spoke about time sharing.
So there have been networks people have built where there's a passive network, so wavelength channels that are assigned to pairs of users. You can do that. There's also active wavelength changing. So there is this notion of quantum frequency conversion, which I didn't talk about here. You can take a quantum signal and change its wavelength without affecting its fidelity of the qubits it's carrying. Yeah. So in our heterogeneous quantum network experiments, it has been shown. It's work that my group started long ago, but others have built on it. Yeah. No, it's not violated. So what happens is that in the process of making a joint 2-qubit measurement, the state actually is destroyed. The Alice qubit is destroyed. She consumes her qubit, and the only thing remaining is the half of the entangled bit that Bob had. So, no. It's essentially it's it's not really Star Trek-y kind of a thing, because Star Trek is something different, but it is that the quantum information that was on Alice's qubit, that is the photon or particle or whatever, that now is gone, and the particle that the Bob had, its quantum state post measurement is the same as what Alice had. Arbitrary state. Yeah. I say that I didn't quite hear it. Yes. The teleportation protocol requires it, right? The results of measurement of the two qubits, they need to be classically communicated. In what sense? Advancement meaning you mean how can quantum communication help classical communication? Maybe I'm not following the. Yeah. Right. Oh, I see. The hardware, I think the advances that are needed are, we need to be able to have, very efficient photon pair sources, being able to pick and choose their wavelength, frequency conversion, switching, fast switches. I didn't talk about the switching work here. Being able to not just passively route photons based on their wavelength, but also being able to actively switch. I think those kind of techniques are also important. Again, in fast optical switching, these scattering issues become dominant, so one has to be careful in terms of designing switches. So that's another actually area where there's a lot of work going on in all optical switching, which is quantum compatible. So there's a lot of work needs to be done there.
Any other questions? I guess I don't see any more hands. So let's thank Professor Prem Kumar for this wonderful talk, where he gave us a very nice overview, and hopefully you have gotten a little bit inspired to work on related areas, maybe even work with him. So I think there could be many opportunities. So he's around here for the high tea. You can of course chat with him. But before that, there's a small token of appreciation from our side. Thank you.
Thank you very much. Appreciate that.
So he's here this evening. So if you want to speak to him, please join us for high tea here. Thank you, everyone.